Hello, good evening.
Good evening, sir.
Yeah, hi. Yeah, hi. So what have we done last class? Biomolecules, have we finished or we are left with something? Just a second.
So we did till non-essential amino acids.
Essential and non-essential.
Yes, sir.
Okay. Okay. So we have done essential and non-essential amino acids. And
So,
yep.
so you told send the last class's recording, but it still hasn't come.
Last class recording you did not get.
No, sir.
Just a second. Okay. Okay, I'll send you today after the class. For sure. Okay.
Yes, sir.
There is something.
Because I missed like 5 minutes because of internet connection.
Which part you want actually?
So second.
Second biomolecules 2, right?
Yeah.
So Let me check. I think it is here only. Fine, I'll share, okay, after the class. Okay, so we have discussed essential, non-essential proteins, right? Isoelectric point. Okay. Deuterion we have discussed, no?
Yes, sir.
Yeah, okay. So, few things we'll discuss and then we'll move on to the last part of this chapter, that is the structure of proteins, okay? They won't ask any questions on structure of proteins, okay? And again, I'm repeating you, for this chapter, biomolecules, and the next chapter, that is polymers, okay? Your NCRT is more than enough, the theory, okay? You must study that because all those things I cannot tell you the theory, every single line I cannot dictate, okay? So NCRT you must read out. Okay, so we have discussed isoelectric point last class. There's a relation of pH that you should know, okay? Again, I'll just do this. Isoelectric point is written as PI, isoelectric point. For any amino acids, for example, suppose we have this, any group attached here, then hydrogen, and here we have NH2. Okay. So in low pH, what happens? If the pH is low, means the solution is acidic. Acidic solution, so this protonates this amine group, right? Amino group here. So what happens here? We get NH3 plus. See, the group here will be as it is, and this is COOH, hydrogen. Okay. Now, when you increase the pH here, as pH increases, means we are going toward the basic behavior. As pH increases, right? Solution is becoming basic. So in basic medium, what happens? This COOH will lose H plus ion. Okay. N3H plus CH COO minus H plus, and this group will be here as it is. Now this is the first dissociation constant Ka1 for this particular thing. Okay. Further, if you decrease pH, the pH, then what happens? Here we do not have hydrogen, but here we have hydrogen, right? So this positive NH3 plus that you have, it releases H plus ion and it forms H plus plus NH2 COO minus, and here we have H lone pair on it. Correct? This is what? This is the deuterion, right? Dipolar ion. Dipolar ion. In short, we write it as Di, dipolar ion. This is cationic part, cationic form, cation, and this is anion, anionic form. And this, the dissociation constant here, it is Ka2. So isoelectric point is the point where the concentration of this cation and this anion is equal. That is also we can say. Then only there will be no net movement, okay, into the ion. So that point is the isoelectric point. So what we can write, we also write here We also write here at isoelectric point, okay, concentration of cation is equals to the concentration of anion. This is the condition we have at isoelectric point. That also we have discussed. It is a pH value. You see, as you are changing the pH, cation converts into neutral ion, and then it converts into anion form of it, right? So you must have a concentration where the concentration of this, we must have a pH value where the concentration of this cation and anion is equal. Correct? That point is isoelectric point. Now you see, if I write down the expression for Ka1, Ka1 will be what? It is the concentration of H plus. If you look at the equation, instead of the concentration of dipolar ion, Di by concentration of what? Concentration of cation. The first ionization constant is this. Similarly, if you write down Ka2, the expression of Ka2, it is a concentration of H plus again, then concentration of anion, the second dissociation equation if you see, by concentration of dipolar ion. Okay, so we know at the isoelectric point, concentration of cation is equals to the concentration of anion, and hence we'll write down the expression in terms of cation and anion from these two relations. So cation expression is what? Concentration of H plus into Di, dipolar ion, divided by concentration of Ka1, and this is concentration of H plus, sorry, concentration of Di, dipolar ion, into K2, Ka2, divided by concentration of H plus. Okay, so this Di and Di will get cancelled, and H plus square is what from this equation? H plus square is the product of the dissociation constant of the two equation, and H plus from this expression is root over of Ka1 into Ka2. pH, if you write down, it is half of pKa1 plus pKa2. So this is the pH where the isoelectric point exists, and those pH value I have given in the last class. Obviously you don't have to memorize that, but yes, the expression of pH to find out the isoelectric point, the pH we have is this. Clear?
So,
Yeah.
so can you go back to the previous slide? Yes, sir.
Done?
Yes, sir.
Just a second. Okay. Okay. copy this.
So what is DI here, sir?
Di is dipolar ion, just the short form we are using.
Oh, okay, sir.
Dipolar ion, that is.
So that's only the Zwitter ion, right?
Right. Zwitter ion is dipolar ion only. Two polar end we have, no positive and negative. Done?
Yes, sir.
Okay. Now, like the structures of amino acids I have given you. Apart from that, we have two more structure which is important, and that is this. Write down these structures. We have NH2, carbon COOH, hydrogen, and here we have isopropyl group attached. The name of this structure is valine. Valine, okay. NH2, C double bond, CCOOH. Here we have CH2, and then we have isopropyl group attached here, hydrogen. This is leucine. Proline structure I have given you. Structure of proline. What is the difference in proline and other amino acid structure we have?
So it's
Could you
not
tell me the base?
typical
It's cyclic.
Sorry?
cyclic.
So it doesn't follow the general structure of amino acids.
General structure plus one more difference is there. If you look at the structure, you'll see one more difference there.
So there's like instead of NH2, there's NH. Can you say?
What?
So like in the
See, all the structure, if you see, okay, in all the structure, the amine is 1 degree, yes or no? All the structure you check, amines
Yes.
is 1 degree. Nitrogen attached with only one carbon. But in proline, what happens?
2
It
degrees.
is secondary amine, right? So that is also very important. You must keep that in mind. Basically, if you know the structure, you can understand all this. But you should also keep this in mind that proline is the only amino acids we have, which has secondary amine group attached in it, right? Secondary amine, like nitrogen atom present into this. Correct? Okay. So the next thing we have to discuss here is I want to show you one structure. Okay, I'll just show you after some time. Fine. Okay. So I am done with it. Correct. Okay. Now, like I said, amines, proteins, the basic unit of protein is what? The basic unit of protein is amino acids. Okay. With the help of amino acids, peptide forms, and from the peptide, we get the very large and complex structure of proteins, right? So next you write down the last part of this chapter is the structure of protein. Okay. This part is not important, but since it is there, we'll just go through it once. Okay. Write down, it is formed by joining the carbonyl group, carboxyl, write down, not carbonyl, carboxyl group of one amino acid and the amino group of other amino acids. Carbonyl group of one amino acid and amino group of other amino acid. For example, you see, if I write down this structure, primary amines, so we have NH2C, a group attached here, C double bond O, OH, hydrogen, and this attached with the amino group of another molecule, which is this G2C double bond OOH, H. So this goes under condensation reaction where H2O comes out and this carbon joins with nitrogen. Okay, so the product here is H2NC G1H C double bond O NH CG2 COOH and H. This is just one thing, right? So this compound is called, you see, CONH. This group is amide group, right? CONH is what? It is amide group, right? This bond, we call it as peptide bond, this bond. Peptide bond, okay? And the molecule is known as, the entire molecule is known as dipeptide. Dipeptide. Dipeptide are those molecules in which two monomers are present. So dipeptide molecule has one peptide bond or one peptide linkage. So number of peptide linkage is less than the number of monomer present into this. If you have two monomer, then the molecule is dipeptide. Three monomer, molecule is tripeptide, tetrapeptide, pentapeptide, and so on. Right? The number of peptide linkage in these molecules is one lesser than the number of monomer present into this. We have
So,
dipeptide. Yeah.
so is there any way to get a monopeptide? Like just one?
No. Monopeptide, you are saying?
Yes, sir.
No, not possible. Monopeptide
Okay.
is not possible because we have this linkage is peptide. See, CONH2, this CONH, this linkage is peptide linkage. So it is possible when we two molecules when arranged, when gets into the reaction,
Okay, sir.
right? So like this, you get a linear long chain, right? At this end also peptide linkage, then peptide linkage, this side also peptide linkage. So a linear long chain you'll get, right? In that chain, we have so many peptide linkages, okay? Hence, we call it as polypeptide also, okay? This molecule is also known as polypeptide. So this kind of suppose thousands, 10,000s amino acids combines like this in a straight chain. So we'll get a very long chain, which we call it as polypeptide, in which peptide bond present, okay? We also call it as that this molecule has polyamide linkage. Amide linkage, since we have so many amide linkage, why amide? Because CONH2 is amide group. So this group is what? Amide. Hence we have polyamide linkage into this, right? And from this only, the protein forms. This is just one part of the structure of protein. Protein structure, we can understand in 4 different parts: primary, secondary, tertiary, and quaternary. Correct. So this structure, the long chain straight structure that you are getting here, this structure is what? It is primary structure of protein. Point I'm trying to make is, this is the basic structure of protein. Correct. So protein contains amide linkage or peptide bond, peptide linkage. And hence we also say protein is made up of peptide. Understood this? Done this one?
Yes, sir.
So this structure, when you get a long chain structure, I'll just write down here. A long chain structure you get, and you have a zigzag structure here. NH2, then carbon HZ1, C double bond O attached with the nitrogen through polypeptide linkage N. Then again we have this side, CG2, C double bond O, O, and like this it goes. Right, so it goes like this both sides. Okay, so this is the linear structure we'll get, and this structure we call it as primary structure of protein. If you look at the structure of protein, it contains different types of forces, van der Waals forces, dipole-dipole interaction, hydrogen bonding. I'll show you this structure just a second. This structure you see. This structure is the linear structure of protein. This structure, zigzag structure. In this structure, this carbon-oxygen bond, okay, and NH, this bond and this bond will always be anti to each other, at anti-position.
So shouldn't there be a hydrogen on the second carbon as well, like the second part?
Understood? This is the structure we have. Now I have written this structure this way, but since it is a long chain, so it will be in the helical form. It won't be a straight chain like that. It will be in a helical form. The structure, the primary structure, will be in a helical form. This angle you see, they haven't asked this question before. This angle you see here, here we have peptide linkage, and this side we have peptide linkage, right? So this angle that you have here, this angle and this angle here, it's phi and psi, the angle that we have. This angle we call it as Ramachandran angle. Okay, this angle phi and psi, they haven't asked question on this before, but just name Ramachandran angle. He's an Indian scientist, and the name is given on his name only, Ramachandran angle. Okay, but the point here is what we have. I have drawn this zigzag structure, but the actual structure will be in the helical form, like a spring. Okay, so actual primary structure, I'll show you how it is. Okay.
So,
Yes.
so in the diagram, what was that? CA?
What? Just a second. Just a second. I'll show you. Previous diagram, right?
Yes, sir.
Which one?
So in the middle and then those two sides, yeah. Is that calcium or is that something else?
No. It's just a notation. It's just
Okay.
a
So
notation of the carbon.
phi and psi is the angle between what and what, like that. The unlabeled thing is that G.
Your voice is just a second, Pratyuk. Just a second. Let me plug in the ear. Yeah, tell me.
So phi and psi,
Ah.
those are the angles between like which two bonds?
CONH. So we have this bond and this bond.
Okay, sir.
Correct. So alpha helix structure of this we have, the helical structure is this. This structure you see. This chain that you see, this is that zigzag chain. Like I said, it exists in helical form. So it will be like this. Okay. Okay. So this is the helical structure. Since a straight chain compound, so it exists in this form, helical structure like this, where you see we have this carbon oxygen bond present like this, all three structures given. Here this one, CO, CO. In this we have nitrogen present, which is not visible here because of this dark wedge. But this nitrogen, this hydrogen, which is attached with this nitrogen here, it can form hydrogen bond with this. So this is the intermolecular forces we have into this. When you see this nitrogen has this hydrogen and this oxygen hydrogen bonding over here. Similarly, we have this side also, right? So because of this attraction, it exists in the helical structure like this attraction. And this is the actual representation of the molecule we have. These are the notations. You don't have to draw this one. Okay. Even if you want, you can draw this. Otherwise, you can leave this also. In NCRT, all these things are given. Just only one thing you should know, that this is the alpha primary structure we have, which we call it as alpha helix structure of protein. That is the primary structure, in which the intermolecular force that is present is hydrogen bonding. Okay, so if you draw this structure, the structure will be like this. Like this, it is a structure we have. It is present. Okay, and it contains nitrogen, carbon, carbon, then nitrogen, carbon, carbon, nitrogen, carbon, I'm just writing down the atom here. Bond V, and like this it goes. So it is alpha helix structure of protein, and this spring-like structure, and this we call it as what? We call it as the primary structure of protein. Oh, sorry, the secondary structure of protein. Primary, I have already given you that. Secondary structure of protein. Alpha helix structure. No, it's not. See, the bonding is not that strong. Okay, the bonding is not that strong. If you talk about overall, if you ask me, the boiling point is not that high. Okay, but overall in carbohydrates, you can say that a bit higher than the other things. Okay, this is secondary, and the first one, the zigzag, is the primary structure. Remember always in zigzag structure, NH bond and CO bond in that linkage, peptide linkage, always anti to each other. Okay, a spring-like structure, alpha helix structure is this. Now you see in this also, since we have polar bonds are there because of difference in electronegativity and all. So it's not like this helical structure exists like this. It will also be randomly bent at some point. It's just a small part of it, but when you look at, because 10,000 amino acids are clubbed together, right? So it's a long compound, long chain structure, right? So because of this polarity and electronegativity difference, plus the dipole forces, okay, hydrogen bonding, because of all these forces, the primary structure, or sorry, the helical structure won't be a straight chain, means it won't be straight like this, but it will be bent at some point. Okay, so this structure you see, it is like this. randomly it is bent at points like this. The structure is there, and this is helical only, but bent like this. Okay, so this is why it happens, because of various forces involved into this structure. Various forces involved in this. What are the forces involved into this? We know hydrogen bonding is involved. Because of polarity, we have dipole-dipole interaction also possible in this. And all these are what? All these are very weak interaction forces. Dipole-dipole interaction. Okay. Ions interaction are also there. Correct? Okay. So this structure, which is bent at points like this randomly, right? This structure is the tertiary structure of protein. Okay. This structure is the tertiary structure of protein. Tertiary structure. And we are almost done. Now, this is what, suppose in this structure, we have thousands amino acid present, for an example. 1,000 amino acids club together and forms this tertiary structure. Similar kind of tertiary structure is formed by another amino acids also, right? So this is just the one unit of this, or the one unit or one part of the entire structure of protein. Correct. So this is one tertiary structure. Like this, we have so many tertiary structures present, right? And if you talk about the final one, the quaternary structure, which is the combination or the arrangement of all these tertiary structures around themselves. Okay. So the final structure you see, suppose we have one unit of tertiary structure, which is this. This is suppose one tertiary structure we have, and I have drawn it this way, but it is actually what? It is actually helical. Okay, so if I draw this here, you see, this is helical actually. Right? Helical structures bend at some point like this. Like I said, this is one part of it, right? One part of it. The primary is the tertiary structure, one part. Similarly, we have so many tertiary structures, like I said, which surrounds each other in a pattern. Like, because why they surrounds? Because again, we have charges present at different atoms: nitrogen, hydrogen, oxygen, electronegative difference. So because of dipole-dipole interaction in this structure, plus with the other similar structures, all other tertiary structures surrounds this structure this way. Randomly, you can draw any way. Suppose this is the another structure we have. Another tertiary structure, suppose we have like this, it surrounds this. Just a second. Another tertiary structures we have here. And this also surrounds this structure. This is P1. Suppose this is P2. This is P3. This is P3, P4, P5, and there are so many. Around this also we have another tertiary structures. This type, we get a very long complex structure, and this entire structure, we call it as protein. Okay, so this structure is a quaternary structure, and this is the structure of protein. Okay, all these are helical structures, you see.
So the yellow ones are also are the
Tertiary.
tertiary structures, right?
Another tertiary structures. All these are tertiary structures, and all tertiary structures are attracted towards each other by various intermolecular forces, right? And collectively they gives this structure, the quaternary structures of protein. Yeah, so a structure based question, protein structure, they do not ask in the exam. They generally ask about some forces involved into this, and linkage, that is amide linkage, we have peptide polyamide linkage that we call it as. Okay.
So,
Yeah.
so in the previous slide, you said the force is responsible for dipole, right?
The previous one. Now all kind of forces are present.
So, but
We,
dipole is very weak, right? So how will that bend?
all forces are very weak. In fact, all forces are very weak. Hydrogen bonding is not a very strong force. Dipole is very weak.
So then
Iron,
how does that bend the structure if it's very weak?
it's a very long structure, no, very large structure. See, suppose you have a rope, right? Very long rope. You cannot keep it straight, no? It's very difficult to keep it straight. So at some plus there are charge separation also. Okay.
Yes.
And it's helical. Because of helical, I have that is the purpose I have shown you this structure. It's helical, and that's why you see, if you look at this one here, in this layer we have CO bond like this, and in this below layer the nitrogen hydrogen bond is what? In the anti position. This hydrogen this side, this CO bond this side. So this side we have this attraction. So because of this attraction only, it bends like this and gives helical structure. Right. So this attraction we have similar. Suppose we have another layer also present like this. Charge separation is there. So obviously positive, negative, whenever they are at the negative charge present at a certain distance, they attract each other. And because of that only, they surrounds the tertiary structure and gives you the quaternary structure of protein.
Yes, sir.
Correct. So this is the structure of protein. 4 different types: primary, secondary, tertiary, and quaternary. Primary is zigzag, secondary is helical. Okay, why helical? Because first of all, long chain and interaction, hydrogen bonding, another interaction, right? Tertiary is what? Tertiary is the bending of this helical structure because of, again, various forces involved. And when these tertiary structures surrounds by the other tertiary structures, that is the quaternary structures, and that is called protein. Very complex structure, correct? In the book, they have drawn the structures also. Okay, if you look at the structure, you will understand how these things are there. Okay, how the cross-linking are there. Okay, one more term that they ask sometimes in the exam, in this, write down denaturation of proteins. Write down denaturation of proteins. Write down the protein present in biological system with a specific configuration and the biological activity of protein is known as native protein, NATIVE, native protein, and the biological activity is known as native protein. The native protein is considered to be denatured, DENATURAD.
So can you repeat the last part?
The native protein is considered to be denatured. D-E-N-A-T-U-R-E-D. This means what? If you do any physical or chemical change, okay, then the higher structure may change. Under any physical or chemical processes, the higher structure of protein will change, but the primary structure, that won't change. Okay, that is called as denatured protein. So write down into this. This means on being subjected to physical or chemical treatment. This means on being subjected to physical or chemical treatment, on being subjected to the chemical treatment, the higher structure of protein may change. The higher structure of protein, higher structure means tertiary or quaternary structure may change. Secondary also to some extent it may change. Okay. The higher structure of protein may change without upsetting the primary structure. Okay, without upsetting the primary structure. Okay, so usually what happens, denatured protein are those protein in which the primary structure does not change. It will be as it is. Higher structure may change. Okay, denaturation is what? It is the protein in which the primary structure also changes, right? So write down in denaturation, next line, in denaturation of protein, in denaturation of protein, the primary structure gets changed okay, primary structure of protein may change. For example, write down the clotting of egg. When we boil it, the clotting of egg is the example of denaturation of protein. Okay, the primary structure changes and hence the egg clots, right? So this process, this denaturation process is irreversible actually. Okay, we cannot go back to the original structure of protein. So it is irreversible denaturation, we call it as. Okay, reversible denaturation is also possible, right? For that we use some agent, okay, some upsetting agent. Whatever the upsetting agent is there, if you detach that, okay, from the structure of protein, you can get the original structure of protein. That we call it as, in that process it is known as reversible naturation of protein. Okay, reversible process it is. Okay, the process of getting the original structure from the denaturated one is known as renaturation. R-E-N-A-T-U-R-A-T-I-O-N. The only thing important in this is what is denaturation of protein. Okay, what happens in this, that is it. Okay, so on a change, physical or chemical processes, if you go through, then protein primary structure usually does not change. That we call it as natured protein. When the primary structure changes, for example, clotting of egg, then it is known as denaturation of protein. Okay, So denaturation may be of two types: irreversible, reversible, right? Reversible when it is possible, when the agent that we have, the upsetting agent which upsets the or which changes the primary structure of protein, if you detach those agents, then the original structure may restore. That we call it as reversible process. Okay, reversible denaturation. Okay, so this is the protein structure we had to discuss. Again, I'm telling you, okay, the only this thing, NCRT is more than enough for this chapter. Nothing you have to read much into this. Okay, biomolecules plus polymers. Okay, both chapter they probably ask one question. Okay, nowadays since we have only 25 questions they are going to ask in chemistry, so these chapters are not that important. So I would suggest you must go through the previous 10 years question. Okay, and based on that only you find out the important topics and you must focus on those, because if you study so much, there are so much theory into this, so much structures and other things you have to memorize. Okay, for just one question or probably not that also, then you have to be very specific what is important and what is not important. Okay, so NCRT plus 10 years, 5 years, last 5 years is also fine. Previous year questions, okay, JE, or you can go through NEET questions also, you can solve for this chapter. Okay, similar kind of questions they ask in NEET also. Fine. Okay, so we are done with this. The next we have to start with polymers. Okay, write down the heading. In this chapter also, we'll see how polymerization takes place, but reaction based question they won't ask. Okay, they mainly ask what is the monomer of this particular polymer, structure of monomer, okay, and uses of this. Okay, uses they usually do not ask in JEE exam, but other exam if you write VIT BITSAT, then uses they ask. Okay, so what is polymer? Polymer is, we all know, it forms by the combination of two or more different or same types of compound that we call it as monomer. Okay, so one by one we'll see this. Write down first of all polymer. The simple molecules from which the repeating structural units, the simple molecules from which the repeating structural units are derived are called monomers. Are called monomers, and the process by which these monomers are converted into polymers are called polymerization. The process by which these monomers are converted into polymers are called polymerization. Correct? So, first of all, what is the use of polymer? Any example of polymer could you give me?
So polythene.
Polythene and see the plastic bottle that we use, the water bottle, that is also made up of polymers. Carry bag, polythene, like you said, polymers. Okay, electric wire, polymers. Okay, that pipe that we use, the
PVC pipe.
PVC, right? Pipe that we use, that is also polymer. Non-sticky cookware you see, it's also polymer. The layer that is coated onto that surface, the black color layer, okay, that is also one kind of polymer. The handle that we use, pressure cooker handle and all, insulated material, that is also one kind of polymer. Okay, nowadays that the travel bag that we use, okay, those things, that is also polymers. Okay, pen in your hand, that is also one kind of polymers. Okay, the keyboard you see, it is also one kind of polymers. Okay, so we have basically huge application of polymers in our day-to-day life. Okay, bucket, polymers, correct. Car, bikes, seat that we have, seat cover, that is also polymers. Okay, so there are so many applications and uses of polymers we have in our day-to-day life, correct. And that is the purpose we are having this chapter in this grade. Okay, suppose if you get interest into this and if you want to pursue this some higher, if you do some research into this, then you have a very good career option. It is actually all these polymer industry, okay, they always have a very good career option, because I have given you so many examples that you see. Fiber chair that you have, again one kind of polymer. Okay, so still the research is going on. Okay, uh, to get different properties of polymers which we use for different purposes, right. Polythene, you see the tensile strength is not that great. Okay, so we have processes by which we can increase the tensile strength, and then we can use for different purposes, right. So depending upon the uses, switchboard, all these things are polymers only, correct. So depending upon the uses, will will have the tensile strength of polymers that we can increase or decrease by the various polymerization techniques. Okay, so that is why we are using this, we are having this particular chapter in our syllabus. Okay, fine. Now you see polymers definition we have seen. We have one simple unit, that is monomer, and when it combines with n number of different units, we'll get the entire structure of polymers, correct. Now polymers, we have various classification. In this chapter, what we have to do, you have to know what type of polymer is it, plus what is the monomer we are using over here for to make this polymer, and the structure of that monomer, plus the uses of that. Okay, these 3-4 things you should know. Okay, fine. So polymers, the classification of polymers have been done in 4-5 different ways. Okay, so first of all, you write down the classification of polymers. Classification of polymers. Example I did not give you. Write down the example. I have already told you. Example, we can have PVC, we can have bakelite, we can have polythene, polyethylene also we call it as. Many examples we have. Okay. Next, write down classification of polymer. So classification of polymer, we have different bases for this. First is, write down the classification based on sources. Based on source. You see, based on source, I won't give you the entire, the theory of it. This important thing I'll write down. Based on source, we have 2 types of polymers. One is natural. What do you mean by this natural polymer? The second one is synthetic polymer.
Natural source.
Sorry?
It comes from a natural source.
Which occurs naturally. Okay, synthetic are man-made. Okay, these are man-made polymers, and this is occurs naturally. Examples are important because they may ask you, they'll give you 4 options, and they may ask you which one of these is natural polymer or synthetic polymer, like that. Okay, so example of natural polymer, you write down We have starch, cellulose, proteins. We have starch, cellulose, proteins, etc. Starch, cellulose, proteins. Synthetic are man-made, and the example is, write down polythene, PVC, nylon, etc. Polythene, PVC, nylon, etc. Okay. Now classification based on structure. I'll just write down based on structures. Based on structure. The first one in this is linear polymer. Linear polymer, write down. These are the polymers in which the monomers are joined together. These are the polymers in which the monomers are joined together to form long straight chain polymer molecules. Long straight chain polymer molecules. Okay, long straight chain polymer molecules. Okay, the example of this, write down. Write down high density polythene. High density polythene is linear polymer, but you see the low density polythene is branch chain polymer. Okay, so these two difference, we have important example. High density polythene, nylons, polyesters are linear polymer. High density polythene, nylon, polyesters are linear polymer. Right, on these polymers has high melting point and high tensile strength. High melting point and high tensile strength. Okay, linear polymer means we have a linear structure, it is right. There's no cross linking. That also you can write here. No cross linking. You understand what is cross linking? When the two layers are joined by some forces, okay, by some interaction, if it is there, that is cross. I'll show you what is cross linking. Here we have this polymer. You see, this is the polymer we have. Linear structure, no cross linking into this. Okay, if these two are joined like this, then there is cross linking. Okay, these are the linear polymers. Layered structure we have, one after the other layer is present. Okay, layered structure. And since cross linking is not present, these are what? These are viscous also. It can slip over the next layer on this. Next, write down branched chain polymer. Second
Sir,
type.
could you repeat the examples for linear?
Example is high density polythene, nylons, polyesters.
Thank you.
Yeah. Okay. Next, write down branched chain polymer. Branched chain polymer. Branched chain polymer are those polymers in which branches are present. Okay, simple as the name suggests. So in this one, we have a linear chain like this, and at some point there will be branch present. Like this, the branches are present. Like this, linear chain and branches are present on this. Write down, in these polymers, the monomers are combined together to produce a long chain polymer, along with the branch along the main chain.
Sir, could you repeat the
These in this polymer, they are the polymers in which monomer units are combined together to form a long chain polymer along with the branches along with the main chain. Branches along with the main chain. Like this, we have a long chain compound and branches present at various points. Example for this is, write down low density polythene, One example we have discussed, amylopectin. Amylopectin branch is there. Glycogen, another example. This has low melting point and low tensile strength.
So it is amylo.
Pectin, PECTIN.
Okay.
Amylo. In starch, we have discussed amylose and amylopectin. Amylose are what? Amylose are the linear chain compounds. We can take this example of amylose in the first one, linear chain. Amylopectin is the branch chain compound. Okay, amylopectin. Next one, the last one is glycogen, Dhruv. The example is amylopectin, low density polythene, and glycogen, GLYCOGEN, glycogen. Okay, third type of compound here is, write down three-dimensional polymer. Three-dimensional polymer. Yeah, right. Right, Azvik, correct. Three-dimensional network polymer also we call it as. Okay, so three-dimensional network polymer is what? We have linear chain, obviously. In linear polymer, what happens? We have chains like this, stacked one on another, like this. But in three-dimensional, what happens? These chains are joined together by cross-linking. Okay, we have cross-linking present into this. These are the cross-linking present we have. Okay. This is three-dimensional network polymer. Very complex structure it is. Write down, in these polymers, the linear polymer chains are joined together to form three-dimensional structure in this polymer. Cross-linking are present. This is the cross-linking. Cross-linking is present, and hence it is also known as cross-linked polymer. And hence it is also known as cross-linked polymer. Example of this type you write down. We have bakelite, then we have urea formaldehyde polymer, we have melamine formaldehyde polymer. On this melamine, they have asked question in JE, okay, on the structure of melamine. I'll show you what structure it is. Okay, later on we'll see this.
So,
Yes,
so these are linear polymers only, just that they're cross-linked, right?
yes.
So linear polymers are like two-dimensional, right? So how does this cross-link make it three-dimensional?
See, you have this structure, correct, and it looks like one after the other, right?
Yes,
But
sir.
it is a very complex structure. It is present in all the three dimensions. Actually, I cannot show you all the three dimension over here, but
So
it
do you
is
have a
present
picture of
along
it?
all the three axes. Yes, three-dimensional structure it is. Here it is 2D, the structure is, but
Yes, sir.
this kind of cross-linking is present in all the three, along all the three axes.
Okay, sir.
Okay, so it is like, you see, first of all, it has branch also present into this, no, like this. Means basically, if you mix 1 and 2, you'll get the third type, and that's why it is three-dimensional.
Yes, sir.
Branch also present, and that branch contains another chain, right? And that contains another chain plus branch also there. So like this, it is present in all the three, along all the three axes. Hence, it is three-dimensional structure.
Yes, sir.
Okay, example you must remember. Okay, these polymers are hard and brittle also. Okay, example you must remember. All these properties they won't ask, but they definitely may ask you that this polymer is what, linear, branch, or three-dimensional, like that. Okay, so third type of classification we have based on synthesis, how these polymers have been formed. Just a sec, Advik. See, you can take that also, Advik, as a polymer, because in that phyllidine we have many carbon atoms present, right? You have one unit which is repeated, but the structure is complex, right? So you can consider that as a polymer which has only one type of monomer present into it. Got it? Anything you see, like, fibers, the cloth that we have, that is also one kind of polymer. Structure we can talk about, we have similar structure or complex structure, but yes, it is a kind of polymer. Okay, now the next third type we have classification based on synthesis. Okay, in this we'll talk about reactions. In this we'll talk about reactions. Okay, so we'll discuss these things in detail after some time. I'll just write down here. One type we have additional polymerization. Addition polymerization could be like we can have free radical mechanism, free radical additional polymerization possible. Additional polymerization. I'm just writing down the name here. I'll show you this mechanism later. The second type we have cationic polymerization. And the third one we have anionic polymerization. Okay, we'll just go through free radical ones. Okay, cations and anions are similar. In cationic polymerization, cation forms. In anionic polymerization, anion forms. Okay, like I said, this example or the reaction based question they won't ask in this chapter. Okay, not tough also, we can discuss but not required. Okay, free radical mechanism, we'll see how the reaction proceeds. It's exactly same. Chain initiation, chain propagation, chain termination. Okay, we'll just go through once. This is additional polymerization. The example of this you write down. Again, the example we have polyethylene, that is polythene, PVC, polyvinyl chloride, examples of additional polymerization. Second one we have condensation polymerization. This also we'll see what is condensation polymerization. Condensation polymerization is the technique in which obviously polymerization takes place plus smaller molecules like NH3, H2O, HCl eliminates in the reaction. Okay, so write down the definition in this. In this type of polymerization, smaller molecules like H2O, NH3 eliminates. Example write down.
So could you repeat the previous part?
In this type of polymerization, smaller molecules like H2O, NH3, eliminates. Example write down. Example we have nylon 6,6. We can have bakelite.
So what does 6,6 mean?
I'll discuss this in detail. Just write down the definition here. Nylon 6,6. This is one name, nylon 6,6. Bakelite. We can have all those urea formaldehyde, melamine formaldehyde polymers. All are examples of condensation polymerization. Okay, next, fourth type of classification based on based on the mode of polymerization. Polymerization. Mainly we have two different types into this. One is homopolymer and the other one is copolymer. Write down homopolymer. It is the polymer forms, homopolymer, it is a polymer forms by single monomeric unit. It is a polymer forms by single monomeric unit. Okay, only one monomer is present into this. Okay, so homopolymer example is polythene again, PVC, polyvinyl chloride. Only one monomer we use into this. We have polythene, polyvinyl chloride. Okay, we can also have polystyrene, etc. Homopolymer. Copolymers are what? It is the polymer in which two or more monomers are present. Okay, different monomer we are using. So write down, these are the polymers in which two or more different monomeric units are present. Two or more different monomeric units are present. Are called copolymer. Example of copolymer, write down nylon 6,6, nylon 6,6. I'll write down the example. Wait. Nylon 6,6, then styrene, butadiene rubber, then urea formaldehyde polymer, bakelite. All these are examples of copolymer. Okay, and the last classification we have based on molecular forces, like the molecular forces involved in this. First type we have elastomers. Write down, these are the polymers in which the intermolecular force of attraction between the polymer chain is the weakest. Weakest intermolecular force we have here. Okay, weakest intermolecular force, elastomers. Properties, write down amorphous. These are amorphous polymer.
These are amorphous polymers and have high degree of elasticity. Examples, write down. Natural rubber, vulcanized rubber. That is SBR. Styrene butadiene rubber, this one. SBR, styrene butadiene rubber. Styrene butadiene rubber, we also call it as BUNA, Buna S. Both are the same thing. Now, vulcanized rubber, okay, this is just one term we have, vulcanization of rubber. That just definition you need to understand. What is vulcanized rubber? Okay, in this only you write down vulcanization. We'll just finish it over here only. Write down the tensile strength and elasticity of a natural rubber can be increased by the process called vulcanization. By the process called vulcanization. Okay. Next line. In this process, by the process called vulcanization. Next line, write down. In this process, natural rubber is heated with 3 to 5% sulfur. 3 to 5% sulfur. Okay. So what happens when we heat this with sulfur? Okay. So first of all, one very common question they ask in this, in vulcanization, what we use? Answer is sulfur, right? So suppose we have a polymer chain like this. This is natural rubber. When we heat this in presence of sulfur, 3 to 5% by weight sulfur we take. Then cross-linking takes place. Randomly, you can draw any structure here. Cross-linking takes place and it has disulfide bond like this. This is cross-linking. Okay. So this rubber, where we have this disulfide bond cross-linking, we call it as vulcanized rubber. Correct. This is vulcanization process, and vulcanized rubber is this, which contains sulfide disulfide linkage with it. First one, classification based on molecular forces, is elastomers, where the intermolecular forces is very weak. Fibers, next one. In this, we have a strong or a strongest intermolecular force. The first one is very weak. Here we have strongest intermolecular force. Write down the polymers in which the intermolecular force of attraction
So,
yeah.
so in the reaction, it was only 3 to 5% sulfur, right? So, but in the molecule, almost everywhere sulfur is found. How is that 3 to 5%?
It's a mass percent, right? So by mass we'll take 3 to 5% sulfur.
Oh, okay.
Okay, so I have drawn this randomly. No, there's no measurement of it. But depending upon, that's why the percentage is depending upon the rubber mass. Okay, the amount of sulfur which is required is 3 to 5% only, so that we'll have this cross linkage possible.
Yes,
Okay.
sir.
It's not like we have one sulfur atom, or S8 we have here, there we have so many sulfur atoms present. It's just a representation. Okay, so the actual structure will count the amount, and accordingly we'll use it.
Yes, sir.
Okay, so fibers, write down the these are the polymers in which the intermolecular force of attractions are strongest. These forces are due to either hydrogen bonding or dipole-dipole interaction. Okay, hydrogen bonding or dipole-dipole interaction. So you should know where we have H bonding present or where we have dipole-dipole interaction. Okay, so the example is in case of nylon, right? If you take nylon example, write down. In nylon, we have hydrogen bonding present. The intermolecular force is hydrogen bonding in nylon. Nylon, we also call it as polyamide because we have amide linkage into this. We'll discuss all these structures. When we finish this classification, we'll discuss all these examples one by one. What monomer we are taking and what is the polymer we are getting, plus uses. Okay. Nylon is also polyamide, hydrogen bonding present into this. Okay. If you talk about polyesters, okay, in this we have dipole-dipole interaction. Dipole-dipole interaction. Polyester is a general name. Some examples of polyester we have terylene, we have polyacrylonitrile, these are some polyesters. Write down these, the two properties. These polymers have very high tensile strength and high melting point, and least elasticity. Okay, high tensile strength because intermolecular forces are very high. High tensile strength, high tensile strength, high melting point, and least elasticity. Okay, now these are the two extreme we have: elastomers and fibers. Least like weakest intermolecular force and strongest intermolecular force. The other two type we have into this, where the intermolecular force falls in the intermediate range in between these two. Okay, so the third type you write down here. Third type are thermoplastics. Thermoplastic. Write down the definition. These are the polymers in which these are the polymers in which the intermolecular force of attraction the intermolecular force of attraction falls in between the range. So sorry, write down intermolecular force of attraction are in between are in between in between that of elastomers and fibers. Are in between that of elastomers and fibers. These are linear polymers. These are linear polymers which are hard at room temperature and becomes soft on heating. Right? So this is the definition of thermoplastics. Polymers which are hard at room temperature and becomes soft on heating. Okay. Next, write down example of this. We have polythene, polystyrene, polythene, polystyrene, polypropylene, Teflon, Teflon.
So what is spelling of polypropylene?
The monomer is propene over there. See, ethylene, propylene are the common name that we use here. Ethylene is ethene only. Propylene is propene only. Right? Monomer is propene over there. Okay? So polythene, yes, polypropylene, polystyrene, polyvinyl chloride, Teflon, etc. See, thermoplastics, the best, the uses of this is what? The best advantage of these plastics are what? That we can melt it down and we can reuse it. Okay, suppose you have a toy, correct? You can form another toy from that particular material. You can melt it down and form another toy from that. Okay, because it melts on, it gets soft on heating, becomes soft on heating. Polythene, you see, whenever you heat polythene, okay, it becomes soft. Okay, you can stretch this. When you heat polythene, you can stretch this polythene for a certain to a certain extent. Okay, because it becomes stretchable, it becomes its elasticity increases on heating. So this kind of polymers are called thermoplastics, which becomes soft on heating. So you keep on heating it, it melts down, and then we can reuse it for the another purpose. Okay, that is the best advantage of it. Okay, there are some. Just a second, Advik, I'll repeat the example. Just a second. Okay. there are some polymers, okay, in which on like those polymers does not get soft on heating. Okay, so it is very difficult to work with those kind of polymer. Now, work means what? Suppose you have to obtain suppose one toy you have, or one any polymers, one substance you have for that polymer, and it is not in use, it is waste. Okay, so you want to melt it down and reuse it, correct? So thermoplastic, we can do it because it gets soft on heating. But another type that we have, which we call it as thermosetting polymers, that is the fourth type. Okay, these polymers, thermosetting polymers, does not get soft on heating. Okay, so it is very difficult to work with this kind of polymers, thermosetting polymers. Okay, now we have certain organic compounds which we can mix with thermosetting polymers, right? And then we can melt it down. Okay, then it becomes soft on heating. To make it soft, thermosetting polymers, we use certain organic substance which we call it as plasticizers. Okay, so plasticizers, only two things you should know. Few examples, we have 2-3 examples plus the definition, that is it. Okay, so I'll give you the definition of plasticizers, but again I'll repeat the examples of thermoplastics as well, correct? The examples are polythene, polypropylene, polystyrene, PVC, polyvinyl chloride, polythene, polypropylene, polystyrene, PVC, Teflon, etc. All these are examples of thermoplastics. Okay, like I said, another definition, one more term in this you write down, that is plasticizers. Plasticizers. Write down the definition. Those plastics which do not soften very much on heating, those plastics which do not soften very much on heating, can be made soft and workable, Those plastics which do not soften very much on heating can be made soft and workable by the addition of certain organic compounds called plasticizers. By the addition of certain organic compounds called plasticizers. Okay, the example of plasticizers, I am writing down here the general name, and then we'll see one specific examples also. The examples of plasticizers, we have dialkyl phthalates and cressyl phosphates. General name is this. A specific example, if you see, dialkyl phthalates, one of the example of this, we have this compound. We have a ring, and on this we have COO, C4H9, COO, C4H9. See, this is butyl. So dibutyl phthalates, this one is, right? This compound is di-N-butyl. Normal butyl, there is no branch into this. Di-N-butyl phthalates. In short, we write it as DBP, dibutyl phthalates. We can have here octyl also present. For example, you see same structure, COOC8H17, COOC8H17, and this we call it as dioctyl phthalates, DOP, because we have octyl group present here, octyl. Here we have butyl. Cressyl phosphate is what? When we have benzene ring and CS3 present on it. This is what? This is cresol. Remove one hydrogen and add phosphate over here. O, P double bond O, OH double bond. This molecule is cressyl phosphate. It is, in fact, it is orthocressyl phosphate because at ortho position it is present. These are plasticizers. Only 2-3 examples. You must remember this.
Sir, can you repeat the definition? My power went off.
Plasticizers.
Yes, sir.
Yes, those plastics which do not soften very much. Those plastics which do not soften very much on heating can be made soft and workable, by the addition of certain organic compounds called plasticizers.
Thank you, sir.
Yeah. The last type in this you write down thermosetting polymers. I've already explained. Just write it down. Thermosetting polymers. These are the polymers which does not get soft on heating, but undergo a change in chemical composition to give a hard insoluble mass. The hardness of these polymers is because of extensive cross-linking. The hardness of these polymers is because of extensive cross-linking.
So could you repeat the previous sentence?
I said these are the polymers which do not get soft on heating and undergo a change in chemical composition to give a hard insoluble mass or substance. And this hardening is because of what? Extensive cross-linking. Examples write down. Examples are the same thing. We have bakelite, urea formaldehyde, melamine formaldehyde polymers. Bakelite is actually the polymer of phenol formaldehyde. phenol and formaldehyde. Okay, and it is used in the making of pressure cooker handle, right? So it does not melt on heating. That's why we use into this pressure cooker handle now. Okay, we'll see this also. So these are the classifications. Okay, classifications important. Okay, this fourth type is most important. Every type plus example of it. Okay, is most important. Fourth type means classification based on molecular forces. Apart from this, the important one we have mode of based on the mode of formation, right? Mode of polymerization. Homopolymers, copolymers. Those also very important. You should know the examples. Which polymer is homo? Which polymer is copolymer? Okay, these two things are the most important in this one. Okay. Now, like I said, let us discuss some examples, monomers and polymers. Okay. So you see the first one. I'll start with this CH2 double bond CH2. This is ethene and the common name is ethylene. Ethylene. When it goes under polymerization, and for polymerization we need some pressure, temperature and catalyst. When it goes under polymerization, it forms this compound H2C CH2 combines with CH2 CH2 and so on it goes. Okay, so this is what, this is the monomer. The monomer, the polymer of this or the repeating unit is this one. Repeating unit is also very important into this. You'll see the question, they have asked what is the repeating unit of this monomer. This kind of expression you can write. So repeating unit is this only. Okay, and hence the polymer we can write this n times. Okay, this is the repeating unit. Okay, and the name of this compound is monomer is ethylene and it forms this, it is polyethylene, polymer of ethylene, polyethylene. It is used in plastic bag. Okay, used for plastic bag. Correct. What kind of polymer it is, homo or copolymer? What kind of polymer is this, homo or copolymer?
Homo, right?
So homo.
It is homopolymer, only one type of monomer. Correct. Homopolymer. This also you should have the idea. Which one is homopolymer, which one is copolymer. Correct. Okay. Second example you see. Now with reference of this only will go so that you can memorize it easily. What I have done, I have replaced one hydrogen with chlorine, CH, and here we have Cl. Right. And when it goes under polymerization, it forms this CH2, CH, Cl, CH2, CH, Cl, Cl, and so on. And what is the repeating unit? Repeating unit is this CH2, CH, Cl, and this is n times. This is the repeating unit. Okay. The name of this compound, see this chlorine is present at the vinylic carbon. So it is vinyl chloride. Correct. Vinyl chloride. And hence its polymer is what?
Polyvinyl chloride.
Polyvinyl chloride. Okay, PVC. Polyvinyl chloride is used in pipes. Okay, PVC pipes that we use. And this is also homopolymer. Copied?
Third type you see. Hydrogen if replaced by benzene ring. And the polymer of this, I'll write down directly the repeating unit, which is this. N times. Okay. The name of this compound is styrene. Remove hydrogen, add benzene, becomes styrene. This becomes polystyrene. And this is used in plastic box. Plastic box. Again, homopolymer. Fourth one. And instead of benzene, if you place this one, it becomes acrylonitrile. Acrylonitrile, and when polymerization takes place, it becomes polyacrylonitrile. Polyacrylonitrile, we also call it as Orlon. The commercial name is Orlon. Okay, used in fiber to make fibers. Okay, this one is again homopolymer. Next type. If you replace all hydrogen by fluorine, it becomes this, and this, the name is tetrafluoro.
So double bond, right?
Yes, double bond, tetrafluoroethylene. And under polymerization, it gives Teflon. The name is Teflon, and it is used in non-sticky cookware. Okay, all these things are given in NCERT. You must read NCERT. Again, this one is homopolymer.
So what is that word after cook?
Cookware, W-A-R-E.
Oh.
Okay. Now the various polymerization technique I have already discussed: additional and condensational polymerization. Okay. So additional will see free radical polymerization, and condensation polymerization we'll see, and then few more examples we'll discuss on this. So write down next polymerization technique. Polymerization technique, we have mainly two types: additional polymerization, second type we have cationic, and third type we have anionic. Okay, cationic, anionic polymerization are are not that important. One thing just you must take care of: if you have this CH2 double bond CH, and here we have CN, acrylonitrile. Okay, so this molecule does not go under cationic polymerization, because when you remove this double bond, you'll get a positive charge here, and this positive charge is getting destabilized by the minus M effect of this CN group. This kind of question they never ask. Okay, they have never asked this kind of questions, and probably they won't ask. Okay, but once you revise, once you go through the NCRT book from this, okay, you will see over there additional and cationic polymerization. Probably it is given. Okay, I'm not very sure, but probably it is given. But since just an understanding you should have, if they ask anything about cationic or anionic polymerization, you can think of the various electronic effects. If the carbocation is getting stabilized, then it goes under cationic polymerization. If the carbon ion is getting stabilized, then it goes under anionic polymerization. Okay, not much. Okay, it's not important at all also. Additional polymerization. So we are going to discuss here free radical polymerization. Okay, only one type we'll see, free radical polymerization. Obviously, in free radical polymerization, the mechanism is free radical mechanism. Okay, and wherever we have free radical, so it is difficult to stop this reaction. We have no control on such reactions. Difficult to stop. Plus, it is chain growth polymerization. Chain growth polymerization. Okay, how it happens, you see. Suppose we have ethylene, CH2 double bond CH2, and it goes under polymerization, free radical polymerization. So for that we use here a free radical agent. Free radical agent. Free radical agent are those, all the peroxides we can take for this purpose. Okay, peroxides are good free radical agents. Okay, we can take benzoyl peroxide for this purpose. Another peroxide also you can take, benzoyl peroxide. Benzoyl peroxide, the structure is this, PHC double bond O, and then we have peroxy linkage, C double bond OPH. Here we have electronic repulsion, and hence it can easily form free radical here because of this lone pair repulsion. Because of this lone pair repulsion, this bond is weak, and hence the formation of free radical is easy. And that is the reason why peroxide forms this radical. Okay, so when this dissociates, it forms two molecules of PHC double bond O radical. Means the two electron will be there and one unpaired electron, so radical it is. And we know free radical has this property of what? To eliminate neutral molecule to form a new radical. So is this possible from this? Yes or no? See, this one electron comes over here and one electron comes over here. This is possible. So we'll get phenyl radical here. This step is chain initiation step. Chain initiation step. The next step is what? Did you copy this?
So 1 minute.
Okay, just a second. Who is this KTG?
Sir, Keaton, sir.
Keaton.
Kirtan. Acha. Okay. 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 The next step is chain propagation. Okay. This radical that forms in the first step, in the second step, it reacts with the monomer, which is the alkene. CH2 double bond CH2. So in this, we get another radical like this. CH2 single bond CH2 radical, and it keeps on going like this. Okay. And finally what happens, will end up getting this kind of structure, and this is chain propagation. CH2 CH2, suppose we have X time, and then we have CH2 CH2 radical. This is chain propagation. And this finally, in chain termination step, it combines with the similar type of molecule which forms in the first step, and it gives this CH2 CH2 This is the product. Since it is free radical mechanism, so the structure is complex and irregular arrangement. Complex structure, no control, and we have irregular arrangement of this. Examples are polyethylene, polypropylene. Propylene, just what you need to do, instead of ethene, you'll take propene there. You'll get polypropylene, PVC, etc. All these are step growth, chain growth polymers. Okay, free radical mechanism. Done. Okay. Now the next polymerization technique we have, the second one, is condensation polymerization. See, condensation reactions are those reactions in which the smaller molecules like H2O, NH3, HCl eliminates in the reaction. Condensation reaction. Okay. Polymerization technique is what we just heat in this, and what we get, you see this reaction. Suppose we have taken a polymer, which is this C double bond OOH, and here also we have C double bond OOH. The name of this compound is terphthalate acid, and when it reacts with glycol, ethylene glycol. Okay, so when we heat this, then what happens here? This OH and H combines and eliminates at water molecule. Okay, so what we get, you see, the product that we get here is HOC double bond O, C double bond O, OCH2, CH2OH. This is the product we get. Now after this, since it is a condensation polymer, so again you have to add one monomer here and then heat it. Okay, so either you can add acid or you can add this alcohol, glycol. Okay, since we have both end here, you see, this is the acid ka end and this is the alcohol end, right? So you can add any one over here. There is no constraint. Suppose if you add alcohol, the reaction takes place at this end. Suppose you have add here, if you add here acid, the reaction takes place at this end. Okay, so there is no constraint at this step. Okay, so next step, suppose I am adding here acid, HOOC, PHCOOH. Then the reaction takes place here. This H and OH goes out, and the product here would be this C double bond O, and then we have the benzene ring, C double bond O, OCH2, CH2O. Then this O, since this H and OH goes out, so this OH attached with this carbon, C double bond O. Then we have a benzene ring. In the last, we have COOH. Okay, H2O molecules goes out, plus H2. Now in the next step, what can we use? What is the monomer we'll use next in the next step?
Alcohol.
Alcohol. So here we have the constraint. We cannot use acid here. Alcohol, and then again we have no constraint, acid, alcohol, both we can use, and like this will go on. Correct? Here the repeating unit, if you see, it starts from here, and after this you see it is the same unit that you are repeating. Correct? So this is the repeating unit, very important. Okay, repeating unit for all these polymers are very important. Repeating unit is this. Okay, this compound you see, because we have ester present into this, C double bond OOR, ester. Then this side also COOR, ester. Then again ester. There are so many esters group present into this. Hence, this compound we call it as polyester. The general name is polyester. Okay, the name of this one is terylene, TERELYENE.
So which one? The given whichever.
What? No, this compound, the general name is polyester because you have ester present into this.
Okay.
But this compound means terphthalate acid and glycol is terylene polymer we get. Okay. Terylene, the commercial name for this is Dacron. So all these are, you see, there's nothing to understand actually. It's just you need to memorize those names. So terylene is a polyester. Dacron is a polyester. Any way they can ask you the question. Okay. So second thing you see, this is step-by-step reaction. You don't provide this molecule, next step reaction is not possible. Here, you don't provide alcohol, this step is not possible. So this is what, this is a step growth polymerization. Step growth polymerization. Step by step it is happening. So condensation polymerization is step growth. Free radical polymerization is chain growth polymerization. Okay, step growth polymerization. Since it is a step growth, so we can control this reaction. Like I said, you don't provide monomer in the next step, the reaction is not possible. Yes, yes, yes. All these steps we used to heat it, then only the water eliminates. Okay, it is a kind of elimination reaction, so it takes place little higher temperature. Okay, it is, so we can control this reaction. Okay, so terylene is a polyester. Other name, the commercial name is Dacron, right? Important. Okay, done. Okay, we'll do one more example and then we'll take a break. Yeah, just one example. Dhruv will finish this. Condensation will finish and then we'll take a break. Just one example. Yeah. Okay, the another example of this, you see condensation polymer. You also know what kind of polymerizing technique we use for this polymer. Okay, so content is not that big, but they can, there are so many informations that you should know. Okay, like you see this example, the second one. I am taking here adipic acid. Adipic acid is this. And this one, the another monomer is hexamethylene diamine. This one is adipic acid. And this one is hexamethylene diamine. Okay, when it goes under polymerization reaction, condensation polymerization, then this OH and H combines and forms H2O, and the product here is hello, can you hear me?
Yes, sir.
Kritika, what happened? Kritika, I'm audible. Kritika can't hear me actually. Just a second. Okay. This is the structure we get, right? Now the repeating unit is this, from this one to this H, because this H again combines with OH in the next step, right? So repeating unit is this one. You see here, there is a amide here, C double bond O NH. So we call it as polyamide, first of all. because we have amide linkage into this one. CONH, like we have in the primary structure of proteins. We have this kind of amide linkage only, peptide bond. Okay, it is polyamide. Repeating unit is this, and the commercial name of polyamide is nylon 6,6. This is a commercial name of polyamide. So what you should memorize here, it's very, very important. This one is right. The nylon 6,6, its monomer is adipic acid and hexamethylene diamine. Okay. Now, Ruchir, you have asked me why this 6,6, correct? Okay. So this 6 actually, these two number over here, this represents the number of carbon atom in both monomer. Understood, Richard?
Yes, I got it.
Number of carbon atom in both monomers. So here you see we have 6 carbon atom and 6 carbon atom here. That's why it is nylon 6,6. Commercial name is this polyamide. So in nylon 6,6 we have amide linkage, also called it as polyamide. Monomers are adipic acid and hexamethylene diamine. And what kind of polymer is this? It is, again, this one is copolymer, right? Because two different monomer we are using for this. Understood? It is copolymer. What about the previous one? This one, polyester, that is terylene. This is also
Copolymer.
copolymer. So you must have this information, whether it is copolymer or homopolymer.
So the name of the polymer is terylene when we use these two monomers, right?
Yes. Terylene is formed by terpethalic acid and glycol. Okay. Generally, we call it as polyester. Like, because we have ester here, no? It is polyester. So terylene is a type of polyester. Commercial name is Dacron. Okay. Similarly, you see here, it is polyamide. General thing is what is polyamide, because we have amide linkage into this. So nylon 6,6 is a polyamide. Terylene is a polyester. Both are copolymer, and the monomer are these two. Forms by condensation polymerization. So anything they can ask you. Done? Okay, this chapter is complete theory. Okay, guys, so we are left with rubber. Okay, not much things are left. Only just few examples we have to see. One more example after this we'll discuss after the break. Okay, just remind me if I forget. Then we'll start with rubber. And then vulcanization, we have done one catalyst we'll do, that is Ziegler-Natta catalyst, and that is it. Okay, fine. We'll take a break now. And after the break, we'll see one more example, and then we'll start with rubber. Okay. Okay, so we'll resume the session at 6:45. Okay, 20 minutes. Yeah, 6:45 we'll resume the session. Take a break, guys. Yes, Varun, this is also controlled reaction, because step growth, no, we can control this reaction at any step. Okay, let's take a break. Hello?
Yes, sir.
Yeah.
Sir, I had a doubt in the first slide we did today.
Biomolecules.
Yes, sir.
Yes.
Sir, on the third arrow, shouldn't it be pH increases because it's losing another H plus?
pH increases. By mistake, I have written. It should be correct. pH increases. Here also we are increasing. No, continuously we are increasing. Correct. Anything else?
No, sir.
Okay. So this is the another reaction, another example of condensation polymerization. Okay. Some more examples we have in this. I'll just show you. That is Bakelite. Okay, Bakelite, it's not exactly the condensation polymerization, but it is a copolymer. Okay, so Bakelite, you see, it is a copolymer, and it is the polymer of phenol and formaldehyde, HCHO. So this in acidic medium or basic medium, anyone you can take, it converts into ortho and para substituted product because OH here is ortho para directing group, CH2OH, and at para position also we get CH2OH. Why ortho para? Because this is electron releasing group, right? It is ortho para directing because the negative charge density increases at ortho and para position. Hence we get this. Okay, you can understand this pi electron attacks onto this carbonyl carbon and C double bond O converts into CO minus, which takes this H plus, forms this. Okay, so this is the product we have. Okay, now after this, what happens? This further reacts with the another molecule. Okay, these two, this also reacts with another ortho substituted product. Okay, so you see, the mechanism is not important. I'm just writing it down here. A little bit of idea you should have. This plus the another molecule we have CH2OH here. CH2OH and OH. Okay, this pi electron, just a second, I'm getting a call. Yeah, this pi electron also attacks onto this carbon, right? And this reaction is also possible at this position, CH2OH we have here, at this position. Okay, means ortho as well as para position, this reaction is taking place. Okay, so which eventually converts into this molecule. Means we have cross-linking here, like this. This molecule is connected with this CH2. And here we have the cross-linking, CH2 and OH here. You can understand this. This para substituted product also reacts at this position. So you'll get this. And here we have CH2. And this is the long chain we get. this structure where we have cross-linking present like this. This is one chain, another chain, and this is a cross-linking. Like this, we have another chain on the top, and here also we have another chain. So this entire structure is bakelite, and this is a thermosetting polymer. Thermosetting polymer. Only one question they have asked on this. Bakelite is the monomer of bakelite, formaldehyde and phenol. Okay. This is the cross-linking we have. And hence, this is also known as cross-linked polymer. Bakelites are cross-linked polymer. This cross-linking, write down, it does not break down on heating. Does not break down on heating. Hence, it is thermosetting polymer. Break down on heating. Hence, it is thermosetting polymer. It is also an example of what? Example of copolymer. Melamine formaldehyde polymer is this. Structure of melamine, on this they have asked question once in the exam. So structure you must remember. Oh.
So could you move to the previous slide? Just 1 second.
Just a second. NH2, NH2 and NH2. This is melamine. I'll show you this.
Done, sir.
Okay. This is melamine. Formaldehyde polymer, and the structure is this. Structure here, this structure is not important. Structure of this polymer is not important. This is the unit we have of this polymer. Okay. Now, what question they have asked here in melamine? The number of lone pair plus pi bond. In melamine, they haven't given the structure. They have written melamine, the name. Okay. So number of lone pair and pi bond, we have 1, 2, 3, 4, 5, 6. 6 lone pair, 3 pi bond, so 9 answer.
So melamine is this compound, right? The
Is this
polymer.
compound? This compound.
What is the polymer called?
What is the
Polymer called?
This we call it as melamine formaldehyde polymer.
Oh, okay.
Name of melamine formaldehyde polymer.
Okay, sir.
Okay. Okay. Now the last thing we have to discuss here is rubber and Ziegler-Natta catalyst. The last two things we'll discuss. Write down rubber. See, rubber, we also have two types of rubber. One is natural rubber, other one is synthetic rubber. Natural rubber which occurs naturally, obtained from tree. Obtained from tree, which we call it as rubber tree. And the material we get from this tree, we call it as latex, L-A-T-E-X, latex material, from which we get rubber. Okay, this is one we have. The example of natural rubber is polyisoprene. Polyisoprene. As the name suggests, it is a polymer of isoprene. Now, what is isoprene? Isoprene is this structure: CH2 double bond, CH3, CH2 double bond, CH3, CH double bond, CH2. 2-methyl buta 1,3 diene. Okay, 2-methyl butadiene 1,3 diene. This is isoprene. And when we do the polymerization of this, free radical polymerization, it forms this: CH2C double bond, CH single bond, CH2, CH3, and this will be repeated n times. The repeating unit is this. Okay. Now this is what? This is polyisoprene. Polyisoprene. Now the important thing here, that across this double bond GI possible, right? So it has two forms. One is cis, other one is trans. Because across this geometrical isomerism possible, trans form of this is comparatively hard, and this cis form is comparatively soft. This is soft, this is hard. And the soft form is used in rubber. Trans form, we call it as gatta parcha. Gatta parcha is that, you have seen that toothpick, right? Plus in RCT, we use a similar thin stick type of thing which we use to fill that stuff into that tooth, right? Root canal treatment, RCT. Okay, so that thing is made up of gatta parcha. Toothpick is an easier example we have, gatta parcha. So they have asked this question also and this question also. Trans form of this we call it as gatta parcha, PERCHA, and cis form we use in rubber. Okay, this is isoprene, and isoprene is a natural rubber. Okay, now synthetic rubber are man-made. Done. Okay, next write down synthetic rubber. This is man-made. Example first one, butadiene rubber. butadiene rubber, and obviously the monomer is butadiene. Monomer is butadiene, and the structure is this, which is polybutadiene. This is polybutadiene. This is also geometrical isomerism possible across this double bond. Okay, but they never ask any questions on this. Okay, but GI possible across this. Second example of this, we have neoprene. Neoprene is the name of the polymer, name of the rubber. No, that doesn't matter, Varun. Okay, that doesn't matter.
Sir, in the structure of polybutadiene, you only put one double bond.
Sorry, what?
Sir, in the structure of polybutadiene, you only put one double bond.
Your voice is not coming properly.
No, sir, in the structure of polybutadiene,
A bit louder.
put only.
Tell me.
Sir, in the structure of polybutadiene, you put one double bond only. That's what he was telling.
There will be only one double bond.
No, in the polymer we have more like double bond, because this is just a unit. Now this is the monomer. Sorry, this is the repeating unit. So like this, we have one more unit this side, then this side, and then this side, and this side also. But across this double bond, GI possible. Are you getting me?
Yes,
this
sir.
is just a repeating unit, no? So this kind of unit will be there.
In one unit, there will be only one double bond.
Only one double bond, one unit. Because it is again a free radical. This comes over here, this comes over here, one double bond, and this side we have the open. One repeating unit. In the repeating unit, we have only one double bond, but in the polymer, we have so many double bonds present. Okay. Right. So neoprene, again, the another the name of the rubber. It is the polymer. It is not monomer. What is the monomer of neoprene? Neoprene, the monomer is chloroprene. Chloroprene, the structure is this: CH2 double bond, C, Cl, CH double bond, CH2. This is chloroprene, the monomer. And from this, we'll get the polymer, and the repeating unit of the polymer is exactly a similar way you can write down: C single bond, CH2 single bond, C double bond, CH single bond, CH2 open bond, and chlorine here. This one is what? This one is polychloroprene. Polychloroprene, the polymer of it, and its commercial name is neoprene. Done?
So just 1 second. Yes, sir. Done.
The third one is styrene butadiene rubber. The polymer of this is styrene. Styrene is this. Butadiene is this.
So this is also man-made only?
Sorry, what?
So this is also man-made or natural?
This is also what? Your voice is not coming, Rahul.
So is it man-made? This one, so like synthetic?
Synthetic rubber. Third example. Right? Third example of synthetic rubber. So this, here the catalyst we use Na. Okay. And when we heat this, we'll get a polymer of this too, which is nothing but this. This is the polymer we have, correct? So we are using sodium as a catalyst here. As a catalyst, correct? And this polymer, we call it as styrene butadiene rubber. The name is that only. In short, it is SBR. Now we also call it as BUNA-S, B-U-N-A-S, where this BU stands for butadiene, S stands for styrene, and Na is the catalyst, that is sodium.
So what does the sodium do here?
Sorry?
What does the sodium do?
See, actually, we are not discussing mechanism, right? So sodium, generally metal, wherever you have, it releases electron, right? And helps in the formation of free radical, right? So this side, what happens when it goes over here, right? So one side you'll get an anion and other side you'll get a radical. So these two combines and further the reaction proceeds. So basically we can say wherever the metal we have, it releases free electron, right? And the free electron, either it forms radical in the reaction or it forms carbon ion. So that is the intermediate of the reaction and the reaction proceeds. So basically, answer for your question, we can say that this metal we are using, which helps in the formation of the intermediate. Okay, composition here, not important, but you can write it down. 25% of styrene we take and 75% of butadiene. Okay, BUNA-S, butadiene, styrene, sodium, BUNA-S. Last example in this one, the synthetic one, is acrylonitrile butadiene rubber. The fourth one, acrylonitrile butadiene rubber. Acrylonitrile is what? Instead of benzene, we'll add what?
CN.
CN, cyanide. This is acrylonitrile. Plus butadiene. Exactly same, just you remove that ring and attach CN. Sodium is the catalyst again we are using. So the structure is CH2, single bond CHCN, CH2, CH double bond, CH single bond, CH2, and this is the structure we have. Okay, this is acrylonitrile butadiene rubber, or we also call it as BUNA-N. Same thing, butadiene, sodium catalyst, N is the nitrile group. All these examples you see, this one is again a copolymer. Previous one, again, it is a copolymer. Write down this copolymer, homopolymer. Copolymer. This is what? This is homo, this is also homo. Both are homopolymer. Done?
Yes.
Okay. Now the last thing, last part of this chapter, the last small you need to understand here is this catalyst, and we call it as Ziegler-Natta catalyst. Ziegler-Natta catalyst is this. It is the mixture of TiCl4 and trialkyl aluminium, AlR3. This is Ziegler-Natta catalyst. Sometimes they ask this formula directly. What is Ziegler-Natta catalyst? TiCl4 and AlR3. Now, what is the use of this catalyst? Obviously, the mechanism is not there. Okay, the use is what I'll show you. Suppose you have polypropylene. Okay. Suppose we have polypropylene. So the structure of polypropylene is this. If you draw the structure, you will get this only. CCH3 H connected with the another molecule CH2 CCH3 H, another molecule CCH2 CCH3 H, and so on. So this is the repeating unit we have. This one or this one or this one, repeating unit. Polypropylene is this. Now when you look at this structure, this carbon is the chiral carbon, asymmetric carbon, chiral carbon we have, and so on. So we have so many chiral carbons present. So when you have this CS3 present this side or this side, that will change the configuration of this compound. Okay, and since the mechanism is free radicals, we do not have any control on this reaction. Okay, so if I write down the structure as this, I'll go to the next page, wait. So if I write down the structure, it is possible that all CS3 present on the same side of carbon atom like this. One possibility is this. Same side of the carbon atom, okay? So when it is present on the same side of the carbon atom, this structure we call it as isotactic structure. Isotactic structure. It is also possible that this CS3 on this asymmetric carbon atom present alternate like this on the same side. Alternate arrangement. This structure, we call it, when we have the alternate arrangement, we call it as syndiotactic. Syndiotactic. And when there is no arrangement, no such arrangement we have, it's randomly arranged like this. This we call it as random arrangement. And when we have random arrangement, this structure is atactic structure. Okay. So in all these three possibilities, the first two structures are regular arrangement. Regular arrangement because we have a fixed pattern here. Regular arrangement because we have a fixed pattern. Okay. And regular arranged structure has good physical properties, which has been observed. Good physical properties observed when the arrangement is regular. Correct? And hence it is useful for the various purposes. Right? Good physical properties, and hence it is useful for the various purposes. Right? This is irregular arrangement. Irregular arrangement. So physical properties are not good. Physical properties are not good. Right? So we always try to avoid this kind of structure which is formed in polymerization technique. Right? So we do not want this kind of arrangement. Atactic arrangement we do not want. Okay. But since it is free radical arrangement, so we do not have any control on this reaction. Right? So mostly what happens, mostly we'll get this kind of arrangement only, random arrangement. Okay. Now to avoid this arrangement and to get regular arrangement, good physical properties of the polymer, right? We use a catalyst, and the catalyst we call it as Ziegler-Natta catalyst. This to convert into regular arrangement. The catalyst we use here is called Ziegler-Natta catalyst, TiCl4 plus Al(C2H5) whole. Any alkyl group we can take. Generally, we'll take ethyl. Okay. So what does this Ziegler-Natta catalyst do? It converts irregular arrangement into regular arrangement, useful to get good physical properties of the polymer.
So,
yeah.
So what do you mean by good physical properties?
Good physical properties means good tensile strength, right? Good high melting point, those things.
Okay.
Stable structure. Done?
Yes, sir.
Okay, guys. So this is it for this chapter. Okay, again, I'm telling you, NCRT is more than enough. You just go through with NCRT, okay? And previous year, at least 5-year questions you see, that is enough for these two chapters, biomolecules. Don't have to put much time into these two chapters, okay? So we are done with this chapter. Next, we are going to start with Grignard reagent and oxidation reduction reaction. Very important reaction. We are going to see what is Grignard reagent. It's reaction plus all the oxidation reduction reaction are there in organic chemistry. So all those things will finish in this chapter. We'll do the reaction of alcohol, aldehyde, ketone, and then those reactions we won't discuss again in those chapter, alcohol, aldehyde, right? So what I'll do, I'll just I want you, all of you, to leave this meeting. I'm sending you the another link. Okay, all of you join that link. Okay, because I have to record this particular session separately. Okay.
Sir, actually, you can like stop recording this and start recording again. It'll be saved as separate files, right?
But I think the name will contains biomolecules and polymers only. That's why I want to do this.
So it'll come as 1 and 2. You'll know the second one's name can
it
be
will come
changed.
as 2 file, but I am not sure with the name of the file. Chalo, we'll try. I'll stop the sharing. So probably we can edit the name later on when we upload it on the YouTube. Okay, anyways, we'll try this. So I'll stop the sharing this, and hopefully I'll get a new file. Just will wait for a few seconds. Okay.
You have to stop recording as well. If you stop recording and then start again.
Yes, that also will do, because again it will be recorded continuously. No, so I'll just pause the. Just a second, guys. I'll just check this. Okay. Let's see. Fine. So write down the heading, Grignard reagent and its reaction. So what is Grignard reagent? We know it is RMGX, correct? RMGX in ether solution. Okay. So Grignard reagent is obtained when alkyl halide reacts with magnesium metal in ether solution, forms RMGX, Grignard reagent. This Grignard reagent is an organometallic compound. We also call it as organometallic compound. Organometallic compounds are those compounds in which we have carbon metal bond present. So magnesium is the metal here, and carbon group is also there. So we have carbon metal bond present. It is organometallic compound. Correct. So this name you must remember. There's a chapter in inorganic chemistry called coordination compound. Okay. In coordination compound, we'll discuss a bit of this organometallic compound also.
So
But
this,
yeah,
the thing which we're discussing right now, like, is it just like generally, or does it come under a particular chapter?
this Grignard reagent.
Yes, sir.
No, like this, you do not have any chapter in organic chemistry.
Okay.
Okay, so I am not following the pattern given in the book. Okay, so like this, I teach actually. Since it is online, we are not following the school curriculum. So I am teaching my way. That is what it is. So if you see all these coaching industry and all, they used to teach like this only. They especially in Kota, they used to teach like this only. They do not take up chapter wise. So reactions of Grignard reagent, and like we did reaction mechanism, we'll see the reactions of all different chapters. Correct. So that is the pattern I'm following. Okay. So in this chapter also you see.
So when we're doing alcohols, we won't be doing this, right?
Sorry.
So when we're doing alcohols, we won't be doing this, right?
Yeah. No. Actually, you see. I'll give you something here. See, from Grignard reagent, we can prepare alkane, right? There's the method.
Yes, sir.
Grignard reagent also reacts with carbonyl compound, right? Aldehyde ketone. From that, it also obtained alcohol. So here we are going to see what is Grignard reagent and what are the reactions of Grignard reagent. Means how do we get alkene? We'll see some reactions of alkene also. We'll see some reactions of alkane also. We'll see reactions of aldehyde, ketone, how alcohol forms from Grignard reagents. So all those things we are going to discuss. So after this chapter, whatever the reaction of Grignard reagent is there in the other chapter, which is left now, we won't discuss those reactions. Are you getting it now?
Yes, sir.
Correct? So that is the only thing.
Okay, sir.
Grignard reagent, RMGX, and you will get you'll get the assignment of this, since there is no any chapter called this thing, Grignard reagent, reactions plus oxidation reaction. So you won't get any separate chapters or questions from this. I have arranged few files, 2 files I have arranged for assignment purpose for this chapter. It will be uploaded in Learnist in few days. Okay, and then you can try those. Anyways, today we are not going to do much, so you don't have to do this now. Okay, after the next class, you can attempt those assignments. Correct? Okay, so RMGX is this organometallic compound. Also, we call it. What is an organometallic compound? This is the compound in which we have carbon metal bond present. Write down. Definition of organometallic compound is we have carbon metal bond present into this. Now we know what? We know Grignard reagent is RMGX. But what is this complex actually? It is a complex compound. And what does this ether do? Okay. So this you understand when you look at the mechanism of this reaction. Magnesium, again, it is a metal. What does it do? It releases what? Free electrons. Okay. Now in presence of free electron, we know carbon halogen bond is what? Carbon halogen bond becomes weak in presence of free electron. How you see this? Because of this electronegativity difference, we have polarity in this bond. And because of this delta positive charge, this electron is attracted towards this alkyl group. And then this halogen takes this 2 electron pair and moves out, forms R radical and halide ion. Is it clear? Any doubt in this? Further, what happens? This radical takes 1 electron and forms carb anion. Clear? Okay. Now, could you tell me what all ions present in this solution now? What all ions are present in this solution?
So R minus,
Sorry?
Mg2 plus and X minus.
Yes, we have Mg2 plus, R minus and X minus. So what happens when you get this negative ions? These ions surrounds this magnesium ion like this. They tries to make bond with this magnesium ion, and this is the coordinate nature of bond, coordinate type of bond it is, like this. Okay. Ether also surrounds this magnesium, this complex which is forming here, with oxygen towards the magnesium ion, positive charge ion like this. Okay, this also surrounds like this. So this complex actually, when we say RMGX is this complex. When we say RMGX, it is Grignard reagent. This and ether surrounds this magnesium ion like this. This is Grignard reagent. Now this complex is stable in an aprotic solvent, polar aprotic solvent. If it is polar protic, then that will break the bond and forms carbon ion. Okay, so in case of polar protic solvent, like suppose H2O, what happens? First of all, this won't stabilize this when we have H2O, ether is not present. So this H2O breaks this bond and forms carb anion. And then this carbon ion behaves as nucleophile or base in the reaction. Did you get it? Attacking particle, basically.
Sir, can you repeat it once?
I said what? Suppose you do not have ether. So if ether is not there, so this complex is not stable. This group won't be there. We have water. So water, what happens? Water reacts with this Mg2+ and forms this bond breaks and forms this carbon ion, which behaves as an attacking particle, nucleophile or base. Correct?
Yes, sir. So, and all the bonds are coordinate bonds to magnesium, right?
Yeah, in coordination compound, we'll have this chapter, we'll discuss it. The bonds between metal and the ligands, which is here R minus X and ether, are coordinate bond only. Okay.
Yes,
See, one more example, if I show you, K4FeCN6, correct. This is also a coordination compound, complex compound. So all these cyanides, 6 cyanide group, attach with coordinate bond with this ion. In coordination compound, the molecule or ion which is written inside this square bracket attached with coordinate bond only.
Yes.
Okay. Correct. So this when we say RMGX is this complex. Okay. And we write this as also this one. RMG, you can also write down this way. RMG 2+ minus minus, or you can also write R minus MgX+. This way also you can write. Both are correct. Okay. Overall it should be neutral basically. Okay. Now one thing you see, we have Rx here. Correct. So if you talk about the rate of formation of Grignard reagent with different alkyl halide, rate of formation of Grignard reagent with different alkyl halides. Suppose we have Ri, Rbr, Rcl, Rf. Which one has the maximum rate?
So Ri will have.
Ri will have maximum because here we have the weakest bond and hence the rate of reaction will be this. Weakest bond. Easier the dissociation of Rx bond, more will be the rate of reaction. Correct? Even this fluoride does not form Grignard reagent, usually, in normal condition. Okay, it's very difficult to break that bond. Okay, this is Grignard reagent. Now you write down next the reactions of Grignard reagent. Reactions of Grignard reagent. See, Grignard reagent mainly shows 2 types of reaction. Okay, it can behave either as a base or as a nucleophile. Nucleophile. Third, one more type we can write down, which I think it can come under this only, but we'll write this separately here only. The third type of reaction we have here, nucleophilic addition elimination reaction. Okay, nucleophilic addition elimination reaction of Grignard reagent. These 3 types of reaction generally it shows. Okay, but we have many reactions with epoxide, aldehyde, ketone, many things we have. Nucleophilic addition elimination reaction. Okay, so basically we have mainly these 2 types. Other types that we have, 3rd, 4th, 5th, there the Grignard reagent is behaving as a nucleophile. Okay, so that may come under the 2nd type. When Grignard reagent behaves as a base and when it behaves as a nucleophile. Okay, so nucleophile, it behaves whenever it reacts with a carbonyl compound. Correct? Aldehyde, ketone and all.
So whenever it reacts with a carbonyl compound, it behaves as a nucleophile. Okay. Behaves as a base. Write down this as a base. Write down when Grignard reagent react with a compound when Grignard reagent react with a compound which has active hydrogen. What is active hydrogen?
So it's hydrogen bonded to like an electronegative element.
Electronegative element, right? For example, we can have OH. This hydrogen is active hydrogen. We can have HF. We can have HCl. HBr also we can take to some extent. NH, hydrogen with nitrogen. Okay, with alkyne, hydrogen with C, triple bond C, alkyne. And even this compound also, it is active hydrogen. Why it is active hydrogen? Anybody can explain this hydrogen?
So will be resonance stabilized.
It will be aromatic.
It will be aromatic. When it loses H plus, it forms what? It forms this compound, the conjugate base of it, which is what? Which is an aromatic compound, highly stable. Hence, this hydrogen is also active hydrogen. Clear? Now, what happens in this reaction? Whenever Grignard reagent reacts with compound containing these kind of hydrogen. So, suppose we have a reaction R minus Mg Cl plus reacts with water. Then this water is behaving as an acid and this is behaving as a base here. So what happens? This R minus takes this H plus, forms RH alkane, and Mg takes this OH and Cl. So it forms an alkane. If you remember, we have done this reaction in alkane chapter also. Preparation of alkane. Got it?
Yes, sir.
Write down one point here. Grignard reagent, when reacts with a compound containing active hydrogen, forms alkane with respect to the alkyl group of Grignard reagent. Okay, so we'll get alkane in this reaction. See this question? Write down the product in these reactions.
Yeah, correct here. So here the product will be methane. Methane and methane. Plus the other product will be MgCl. This one will attach with the negative ion which is left, OCS3. This also attached with OPH. Done. So we always get alkane whenever Grignard reagent reacts with a compound which contains active hydrogen. Always. Correct? Alkane with respect to the alkyl group of Grignard reagent. Okay, this is the first reaction where the Grignard reagent is behaving as a base and the other compound is behaving as an acid. Now, the second reaction we have nucleophilic addition. No. Nothing, no rearrangement we have to consider here. It's an ionic reaction, ionic sort of reaction it is. Okay, neutralization type, very fast reaction it is. Okay, next write down nucleophilic addition reaction. Nucleophilic addition elimination, the third one here, which is also a part of this only. Nucleophilic addition elimination, the third one is. See, it is addition elimination. Write down into this. This reaction is possible with carbonyl compound. Possible with carbonyl compound. For example, you see, if we have a carbonyl compound, C double bond O reacts with Cl minus, what happens? And in this reaction, you see, it is a two-step reaction and we always use H plus H2O in the second step. If it is not given also, we have to assume this. Okay, so this, the first step, the reaction is, you see this R minus behaves as a nucleophile, attacks onto this carbon atom. And why this attack is there? Because this bond is polar, delta positive and delta negative. So when this attacks on this pi electron jumps onto this oxygen and it forms this one. Okay, and to make this ion neutral, we'll write down Mg plus and Cl here, like this. If you don't write this also, it's fine. Okay, now after this, what happens in the next step, H plus H2O, this H plus get attached onto this oxygen in the next step. And we get this plus. The next one is this Mg plus and Cl minus. There the H2O is behaving as a nucleophile, attack onto this, forms this, which further converts into Mg, OH, Cl and H plus release into this. So here the acid that we are using here, it is behaving as a catalyst. It moves out. Okay. So basically what we can say, from H2O, OH attach here on this MgCl, we'll get MgOHCl, and H plus get attached onto this. Okay. So overall, if I write down this reaction this way, this reacts with, in the first step, RMgCl, and in the second step, H plus H2O. Overall reaction is this. It converts into OH, R, yet the key point is, you have to keep this in mind, that this hydrogen is coming from acid, and this is coming from the solvent, which is water here. Right? This point you have to keep in mind. Got it?
Yes, sir.
Done?
Yes, sir.
Okay. Now you see, if you want to write down the product here, what happens? Suppose this is an carbonyl compound, right? So it can be aldehyde. And when it is aldehyde, the product is what? The product is a tertiary alcohol. So the first conclusion of this, ketone with RMgX, H plus H2O is understood. It gives tertiary alcohol, correct?
Yes.
When you take aldehyde here,
Two possibilities, secondary or primary.
then we'll get secondary alcohol, 2-degree alcohol.
So you can get primary also, right? If methanol.
Primary we get when we have formaldehyde.
Yeah, methanol.
Okay, I'll write down that also. When we take aldehyde here, aldehyde with the same reagent, it gives 2-degree alcohol. And the third point, if you take formaldehyde here, if you take formaldehyde, for example, H, and H you have, then for formaldehyde, it is 1-degree or primary alcohol. So this reaction, you see, this is the preparation method of alcohol. Okay. Now again, this reaction we won't do there in alcohol chapter. Clear? Understood? Any doubt in this?
So if we take ketones with two different R groups, will we get enantiomers?
Two different R groups. We'll get RNS, two different form of it.
Okay, sir.
Enantiomers we won't get. We'll get two product into that, RNS. Just a second. It is sp2 now. So both side attack is possible. We'll get enantiomers also in that case. Because you see, it is sp2. So we have equal probability that this will attack from the top and from the bottom. Right. So one gives you R, so other one gives you S. Equal probability, so you'll get enantiomers. Correct?
Okay, sir.
So here also what happens, this carbon is sp2, converts into what? sp3 finally. That is what it means. And this is not chiral, but this may become chiral depending upon the group attached over here. Correct? See, even with aldehyde also you can get enantiomers, possible. But if you take here D plus, then it's possible. D plus D2 like that. Okay, we'll do some examples on that. Okay, write down the product in these reactions. MgCl and H plus H2.
So we have to tell, like, if there's more than one product possible, we have to tell that also.
No, just write down the product. We'll see that whether it is possible or not. But just write down the product. Not all product you have to write. Done? Okay. So since it is a ketone, so we'll end up getting tertiary alcohol, and the product here is OH. Right? Not a chiral carbon, only one product possible. It is again a ketone. Product will be a tertiary alcohol, OH and pH. Here, aldehyde and product will be secondary alcohol, COH, ET and H. Okay, this is the product we get. Other product will be what? It will be same for all the three reaction, MgOHCl. Here also it is MgOHCl, and here also it is MgOHCl. This is the reaction we get, conversion of this carbonyl group into alcohol. Okay. Now suppose how they frame the question here, you see, if you do the acidic dehydration of it, acidic dehydration, then what is the product you get? Acidic dehydration.
Dehydration meaning H2 was out, right?
I think expansion will happen.
Yes, Vikas.
So
Yeah,
you'll get a 5 ring after that.
correct. So first of all, what happens, we'll get H2O plus here. So it converts into this first. OH, H positive charge, ET and H. And then H2O molecules eliminates, forms a carbocation, which is CHET positive charge. And then we have ring expansion. Ring expansion gives you 5-membered ring. 1, 2, 3, 4, 5. So you'll get a 5-membered ring where at the first carbon CH2CH3 group is attached. And we get the positive charge at second carbon, right? So one this and second one is this. Further, what happens? Tell me.
Hydride.
The hydrogen.
Again, we have hydride shift in this. So hydride shift gives you tertiary carbocation, which is this CH2CH3 positive charge. And then what happens in the last?
So we'll get Zaitsev product.
So two possible product. One is this CH3, and another product is this. Which one is more stable?
So said the first one.
Yeah, so the first one.
First one.
More substituted alkene.
Which one is more substituted?
The first one I thought.
The second one.
How many alpha hydrogen in the first one?
So 7.
And the second one?
So 6.
6. So first one is more stable. Correct. So this is how they frame the question. Okay, you started with carbonyl compound and then it forms alcohol and then acidic hydrolysis. Eventually you'll get alkene into this one. Correct? Okay. Now the next reaction, that is nucleophilic addition elimination, will start in the next class. Okay. So we'll have nucleophilic addition elimination, then epoxide reaction, cyanide reaction. Okay, all these reactions we'll see. Okay. So this chapter, you let it be like, you do not have to solve any questions on this for this week. You finished biomolecules and polymers, and the next class onwards will give you assignment on this. Okay.
Okay, sir.
Okay. Thank you, guys.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir. After
Thank you,
this,
sir.
sir, after this, can we start? After this chapter, can we start with coordination compounds?
Coordination. We
Yeah.
can start, not an issue.
Okay, sir. Thank you, sir.
Okay, yeah.